Welcome back, everybody. It's my pleasure to introduce Elisabeth Uhlemann. Elisabeth did her PhD at Chalmers and Halmstad University before Halmstad University had the rights to give PhDs. And her PhD work was on communications theory. After that, she did an industrial PhD at Volvo.
Postdoc.
Industrial postdoc, sorry, thank you. That's what comes after the PhD. And from that point on, she's been doing much more applied work in communications. And now she's an associate professor at Mälardalen University. Welcome, Elisabeth.
Thanks. So sorry for giving part one quite late in the workshop. So I have three different parts, or this is what I promised to say. I needed to look at the abstract I gave Alid to see what I promised. So I'm going to talk about requirements for wireless vehicular communications because there's a specific combination of requirements that are particularly challenging and it needs to be reliable and timely. So that's why it becomes cyber-physical systems. But exactly how reliable or how timely, that depends. And also how to evaluate the performance also differs from traditional communication systems because of multiple stakeholders, among other things. So I'm going to talk about the requirements and also about frequency spectrum because there's some political debates ongoing about this, and give some overview on research in wireless vehicular communications. So this is the part that I promised to. But then I learned it's supposed to be three parts. So I would actually I would like to start with these requirements because it's more fun or lightweight. But I think we need to have a wireless communications crash course first because lots of people, surprisingly enough, lots of people don't do communications, and even those who does, control theory people, they do mostly wires, and it's not exactly the same thing. So I would like to have the motivation first, and then have the boring stuff. But my next slot is this evening at 5 o'clock or something, and that's going to be too tough. So you get the boring stuff now, and the lightweight stuff at 5. So now it's now, and then the research stuff tomorrow. So, wireless communication crash course. And I've given this in very different contexts because I do lots of this cross-disciplinary research. So in some research fields you don't do a lot of math, and in others you do. So I usually have a math version of the introduction, and then I have a picture version. And this time I couldn't decide exactly which. So you get a bit of both, but the heavy math is removed. So you get it in pictures instead. It's not comic strip, but almost. So the general idea about communications, regardless of if it's wired or wireless, is that you want to move information from point A to point B. And you do this with a certain quality. So the quality could be lots of different things, depending on the requirements. So quality could be with a certain delay, or with a certain transmitted power, or with a certain data rate or something. And to do this with a certain quality, the thing that you move is a number of bits. It's a message of some sort. And to do this, you need to pay with something. And the cost of moving a message from A to B it also depends. So it could be actual money, if it's complexity or hardware, but it could also be other things, spectral efficiency or transmitted power or something. So typical quality measures comes from the requirements, and different types of information that is to be communicated have different requirements. So if we take some extreme cases, we can start with voice call. It's extreme because it's very error tolerant. So we can throw away lots of data, and the ear cannot notice because we don't have very high resolution on the ear. Some opera people have higher resolution than me, but still we can throw away things and they will not notice. So the bit error probability, the probability of losing a bit every now and then, is quite moderate. You can throw away some things, but the delay is not. So if it starts to exceed 150 milliseconds, it becomes annoying. That was the time when you used to call Australia from Europe in the past, and you started to speak at the same time. You started sentences at the same time. And that's because we go beyond this 150 milliseconds, and that's really annoying. So it's better to catch up and throw away some things, and then it's okay again. So the delay is quite tough in comparison. The data rate is very moderate if it's just voice. Again, opera is going to be higher data rate requirements, but it's still relatively small. So the other extreme then, that will be emailing. It's very high requirements on bit error rate, because it's enough that you spell the email wrong yourself. You don't want the communication to do it for you, or to rearrange the letters or something. So bit error probability, this is high requirements. But the delay, yeah, so now it's starting to be an old slide. But it used to be about an hour, but maybe now we get annoyed even if it's an hour. But in comparison, we don't notice if it's 100 milliseconds or 150 milliseconds. And the data rate becomes irrelevant because of this. So the other extreme of having high requirements on data rate and then moderate on the two others is if you have mobile broadband, so web surfing or something. So it needs to be fairly low bit error rate, but you can still retransmit if it doesn't work. So that's why you can trade off one for the other one, but the data rate needs to be high, otherwise it becomes annoying. So different types of requirements. And the possible design goals they have for constructing your communication system, it could be that you want to go all in for maximize the transmission rate, so just make it as fast as possible, or have as few errors as possible, or as low system complexity as possible. And some of these things, the design goals, you can just have one and ignore the other ones. But some of them you obtain on the benefit, at the expense. You obtain them at the expense of some other ones because they are in conflict. So then you need to set minimum goals on each of them and then do joint optimization on several ones. So when we want to design our communication system, there are some rules, regulations, limits, and constraints. Some of them are human-made, and some of them are nature-made. So if we start with the nature ones, theoretical limits, there are two main ones, Nyquist and Shannon. So Shannon, he has designed a capacity. Okay. I see the heading is in Swedish, but the rest of it is not, so yeah, you can still detect. So Shannon has designed this channel capacity, the capacity of each channel. So as long as you are below the capacity, you don't exceed the capacity of the channel, you can have arbitrary low error rates. If you go above it, you can't. Everything goes wrong, always. So this is really useful information because you can figure out how far away from the capacity you are. So if you're far away from the capacity, it means you can increase the rate. The problem is that he hasn't told us which codes to use, just that there exists some, but we don't know which ones. So if you want to do pictures above of Shannon, this will be it. So you can't, there's some limit to how fast you can speak. If you speak faster, you can't get anything through. And this is because we have noise in communications, always. It doesn't matter what channel, we always have noise. If we didn't have any noise, then it would be possible to take the encyclopedia, to have the ASCII string of an encyclopedia, and then transform that into zeros and ones, a really long string. And you put 0 point in front of it, then you have lots of decimals. If there's no noise in communications, we could just transmit a pulse with that amplitude, and boof, you would get the encyclopedia on. But we can't, because there's noise. And this comes from electrons moving. So when it comes to be really small or really fast, we pay because electrons move. They are not stationary. So the other one, Nyquist, it comes from the fact that we use filters, low-pass filters, to receive signals. And we would like them to look like this. Then they would be perfect. But then it would mean that we would need to transmit something like this, the sync. And this is not really possible. We can't do... so if you don't have the tails on the side, it means that it will be slanted on these sides. So then it doesn't work. So because they are slanted, you can't push them too much together. So this has to do with the sampling rate. You can't sample too often. So you need to sample in the middle of the symbol. And we can't sample too often because then they would smear together. So the same thing in more popular science thing is that to get the information back, you need to sample in the middle. And if we do it, if these are too tight, they will start to interfere with each other. So if you do it too fast, then they will spill over on the other side. And all of a sudden, this is okay because here we have +1, but if you have a +1, -1, it can turn out to be nothing. So when we don't know. And here it doesn't help. If you increase the transmit power, it will make this intersymbol interference even worse. So this is our natural constraints. Then we have some governmental regulations, and these are mainly for, in some sense it's also for, but mainly for wireless. And so we have in each country some frequency allocations, and within those you have a maximum allowed transmit power, and you can't use too much bandwidth because then you interfere too much with other guys.
Can I ask a question?
Yes.
What's the motivation behind the maximum allowed transmit power?
So whenever you transmit on a frequency, you are also using other frequencies involuntarily. So then there are some rules. So if you want to use this frequency, you can use this transmit power here, but it needs to be below this threshold on this adjacent band where we are not allowed to be. I'll come to more on this on the second part. So just to get an example on this part, we can look at the spectrum allocation in the US. As you can see, it's quite crowded. So if you are transmitting somewhere where you're not supposed to, it's going to be problems. And this is really important because it can destroy lots of useful information. TV and radio and other things, but also military applications. So most of the things, so the lower the frequency, the more they will travel. The higher the frequency, the easier they stop. So there's a reason why we got this 2 gigahertz or 2.4 gigahertz frequency band, because that's the resonance frequency of water, approximately, which means since humans are 60-70% water, we absorb it. So it's really bad to use for military applications. It's absorbed everywhere because they have a lot of water. So that's why they're 3, and everybody can use them. But the ones that are useful, we can't use. So these blue ones are a bit military frequencies, and then you're not allowed to use it. So you need to fit on the other ones, and it's strict regulations. But we have this free bands that are free everywhere. And this is not specific to US. Every country looks the same. And then we have some other technological limitations. So it could be that we need to use existing transceivers that you can buy off the shelves. Or it needs, maybe we have some form factor limitations. So we have some complexity constraints because otherwise it would be too costly. Or you can't use more than this amount of memory, or the battery needs to last for 30 years or something. So these are more like technological limitations. So these are the things that we need to take into consideration when we design communication systems. Quarter past 11, or? Or when did I start, or when do I stop?
You started
I know I have 45 minutes.
10:30, so we have half an hour now.
Ah, good. Okay, so let's go. So these things that I said before, they are valid for any communication. Doesn't matter if it's wireless or not. Now we come into the wireless parts. So if you want to say something generic about the wireless channel, is that it generally has a higher error rate than wired channels or wireline channels. It has a higher path loss. So path loss is the signal strength reduces with distance. So this is higher in wireless and frequency depending. You also have problems with shadowing, something in between the sender and the transmitter. Or you have multipath, the signal bouncing on, taking different multiple paths and combining at the receiver. Because of these things, you have a noise level that varies with time, frequency, and space. And everything is broadcast, whether you like it or not. You can do some things, directional antennas, but it's still broadcasting in a specific direction. So the capacity of the link is typically limited by interference from other users, and these can be intentional or non-intentional. Microwave ovens, for example, are non-intentional. They want to transmit at the resonance power of the water. So if they are not sufficiently isolated or insulated, I never remember which one, then you have microwave energy interfering with wireless transceivers. But the main point is that every channel is unique. Every wireless channel is unique, and there's several wireless channels everywhere, all the time, because they vary with time and frequency and space. So you can't say what's the bit error rate of a wireless channel. It's like saying how long is a road, or how wide is a road, or something. So it depends. So for wires you can say something, so you have some performance, but for wireless you can't. And this is because of the propagation mechanism from the electromagnetic waves. So wireless communication is transmission of electromagnetic waves, and they can reflect, transmit, scatter, or diffract, depending on how it hits the surface and what the surface looks like. So in some cases it just reflects, like in a mirror, or it goes through transmission, or it splits up and scatters all over if it's really rough surface, or it can bend around the corner, diffraction, the same way as you can see the water doing when it comes out like this. So this has some pros and cons. The good thing with this is because it does this thing, you don't necessarily need a line of sight to communicate. So if you communicate with a flashlight or something, you need to have line of sight. So flashlight is also electromagnetic wave, but different waveform. But here you don't need it because it can bounce around and find its way anyway. So this is good. But there has some other problems in that if you have lots of things in between and you don't know about it, it becomes very random, if there's such a thing. And you know something about the frequency as well, because the surface, whether it looks rough or smooth, it depends on who is looking. So it depends on the wavelength. So as long as the surface looks smooth, it will do like this. Or if it looks rough, it will do like this. And the wavelength is this with the frequencies. So if you increase the frequency, you get more optical communication. So if you have your remote control for your TV, this is a very high frequency, infrared. So then you need to aim it towards the TV, so it doesn't spread out so much. But also if you have a higher frequency, you can have smaller antennas. And you have a higher path loss, which could be good or bad. It could be good because then you can fit more communicators in the same area. But it could be bad if you want to reach somebody very far away. So the thing that happens because of these reflections and diffractions is that when you transmit a signal, I would say even regardless if you have a directional antenna or an omnidirectional antenna, it just happens in different angles. You have a signal that is scattered, and all the different parts of the signal will travel different places. Some of them will return to the intended receiver. So you have one going in the direct path, if there is a direct path. And then you have other ones that happens to return to the same receiver. So it's multiple versions of the same signal that comes and arrive at the receiver at different points in time. So they interfere with each other. So if we have this, let's say that the blue one is the desired signal, the line of sight signal, you can have something scattered and reflected and join the antenna at the same time, but it traveled slightly longer, so it's a little bit delayed. So then it looks like the pig signal. So in this case, it's fine. It's actually better than if we didn't have reflections, because these ones will interfere constructively. So whenever it's a +1, the other one will also have a +1, so we'll have plus more. But it could also be that they interfere destructively, or in the worst case, they can be completely opposite. So here they interfere destructively, exactly aligned. So this is called outage. So here you hear nothing. So increase the power, you'll still hear nothing. Doesn't matter. So I have this technician in my house. He wanted to install an alarm system. And he had these wireless sensors that had some indications on where to put them. So if it was a good connection, it was a little green lamp lighting. And if it was a bad connection, it was a red lamp. So he put it on the wall, and he would see if it's a green light or a red light. And then he had it over here. It was a red light, and he moved it over there. It got to be a green light. And then he said, must be something wrong. It's not working properly. Well, it's enough if you move it half a wavelength, it will be constructively. Move it half a wavelength, it will be destructively. It's exactly right. And that's how it works. But he didn't put it up because he said, it doesn't work. And I was trying to say, but it's going to be the same with the other one. But no. So he went to change. Yeah, anyway. So this is called multipath fading. So you have multiple paths, all the signals traveling multiple paths. And then they interfere constructively or destructively, causing the signals to fade and change. So the path loss, because it depends on the distance between the transmitter and receiver, we have signals having traveled different distances. So they have different path loss. So the one that traveled the shortest distance is strongest. This is the line of sight path. So the other ones, they will be weaker. But if there are many, they can still cause trouble. So lots of the things vary with the path loss, and they will have different noise and different phase. So the resulting could look something like this. This is where it's constructively or destructively interfering, and different signals interfering. So then it looks something like this. This is a Rayleigh fading where we don't have any line of sight path at all. It's only this alternative routes. So in the worst case, you can have basically an outage. This is minus 35 dB. It just goes down. Or it could be better. So you could have a higher energy than the transmitter energy because the signals help each other. So this is just the received signal power versus time. But this you can do in more dimensions. So if I put time equal to 1, we can do the same thing and look at different spaces, different places in a room, or at different frequencies. And it will vary like this. Yes?
That means compared to line of sight.
So in this case,
And the previous 0 means
So in this case, I have a Rayleigh fading. So it doesn't say anywhere on the slide, but if you have a Rayleigh fading, it means you have no line of sight.
But what is the reference point?
This is just measuring the received signal power. So I guess the reference point is the transmitted energy.
But 5 dB more than conservation of energy. How can we? Where's the energy coming from? If it's more than that?
Yeah. Still, it's related to this. Root mean square. In theory, it's related to the transmitted energy, but here he uses this root mean square, which is the received nominative. Exactly.
Line of sight.
Yeah. Yes. Hopefully.
Yeah.
Yes. Except that it's not line of sight, but yes, the one that it would be if there was a line of sight. If there was a line of sight. Yes. Good question. Okay, so time equal to 1. If I freeze it, then it will look like this. It will be the same if you freeze frequency and look at different times or spaces. So this is an invented place, but just for the... Yeah. But if you want to look it for... This is what channel model guys do. They go out and measure stuff, and then they find out, okay, here we have reflection, here we have diffraction, and here we have scattering. And then you get these. So if you remember this one, we use the coloring. So red is fairly good, blue is not so good. So you would have things like this, almost like a heat thing. So here it's fairly good, and then it could be really bad at some points in time. So then you have this, and you make a time frequency response. If you look at it from this side, it will look like this. If you just look at it from the top, it will look like this. So here, at this time, using this frequency, really good. Even stronger than what I transmitted. Here, really bad. Nothing comes. Or even less than nothing. So minus 40 dB. So this is what it looks like. And then you can complicate it a bit more. So there are different types of distributions. And people have sort of mapped them approximately to different phenomena. So approximately, if there's a line of sight path, you have a Raysian distribution. And then you can say even more things about the Raysian. Say how strong is the line of sight compared to the reflected path. And if you don't have a line of sight, it becomes Rayleigh distributed. So all the different things in the expression is that you don't know exactly the number of paths that we have. And for each path, there's a different path loss. And for each path, there's a different delay. And if the receiver or the transmitter moves, then you have a Doppler shift as well. So if you don't know all the paths, you just have something approximate, and you assume that these are the most important ones. These 10 ones are the most important ones. The rest we ignore. Then you can do this. Pick a Raysian or a Rayleigh or something. If you know exactly, if you're like in the desert, then you typically have 2 rays. You have the line of sight and the reflected path, two-way ground model. So then it's easy. Or in space, it's easy because there's not so many things.
So can we see this as like ray tracing, basically?
Yes. So that's what I was going to say. If you have very few paths, like in the desert, then you can do ray tracing. But if it becomes too many rays to trace, you just use this and say, okay, above 10 we don't care, and we say it's a Raysian. And so we specify in the Raysian the first 10, and then... So ray tracing is a big thing. And if everything moves, like in vehicular communications, you have these paths, the different paths being born and dying. So there's like a pattern for when they are born and when they die and how long they are, and they change. So all the time the paths, but also the number of paths, change with time. Path loss changes even for a specific path that exists. It varies because you move, and the delay, how the signals are shifted compared to each other also varies, and the Doppler, of course, varies. So you have constructive and destructive interference, multiple propagation paths, and we move around. So you can change from having a really strong received power to a really weak one if you just move half a wavelength. So it's the wavelength or the transmitter frequency that is important. So for 6 gigahertz, one wavelength is 5 centimeters. Metric, sorry. So 2.5 centimeters. If you move 2.5 centimeters, you go from constructive to destructive, or vice versa. So half a wavelength, if you travel at 54 kilometers per hour, half a wavelength, or a wavelength, is 3 milliseconds. So 1.5 milliseconds, constructive, destructive. So this is why it can be challenging to maintain a reliable link. So how are we supposed to use this information? What do we need it for? Well, if you know the situation, you have different techniques to handle the fading. So what you want to do is to hit the red ones and avoid the blue ones. So if the fading will vary with time, space, and frequency, it means that at some places the channel is good, and some places it's bad, but not all the time, and not for all frequencies. So we use time diversity. I mean, this we already know. Somehow we retransmit. People do the same. If you can't hear me, I ask. Or you use different frequencies, frequency diversity or frequency hopping. Or you'd use different places, either by moving or by having multiple antennas, or to do relaying, which I will come to later on. So if you want to do time diversity, you can have automatic repeat request. This is what we do. When we can't hear, then we try to have the speaker repeat. So this is good because you increase the reliability, but you also increase the delay, which could be bad for some cyber-physical systems. So because you have a deadline, maybe you don't have more than 3 trials or something. We can use frequency diversity. An example of this is frequency hop spread spectrum, like the one used in Bluetooth. Then you divide the frequency band that you have in little portions, and these are available all of the time. So each user will use a specific pattern, so you don't use it all the time the same. So this was originally done because for military purposes. So if you use the same frequency all the time, you can transmit a jamming signal on that frequency. So if you use different ones, not everything get ruined. So Bluetooth jumps between 79 different frequencies. And this is good to use even if it's deadlines, because it doesn't take more time. Well, it takes more complexity to jump and do things. So the idea is that you don't actually get all of the frequencies are not equally bad, so only some of them will be bad. And Bluetooth, the more advanced one, they have a blacklist and a whitelist. So if something didn't work out in the past, they will remember, and they will not use this box more. Or they will use good boxes more frequently. Or you can have different users. So if you use on this one, then you reach a specific user. So you can, if everything is good, you can use it to fit more users in the same thing. Space diversity. So you just walk on a different time. This is what we do. We scream at home. If nobody hears, you pop your head out of the kitchen and try again. So at a different space. So this would actually be the case. Now I have one ear on each side, which means I can decide where the person's speaking. So the human system is somewhat less than optimal, because if I want to hear the height of it, I need to tilt my ear slightly. So they are not at the same, they're not aligned equally. So if I had 4 ears, I never had to tilt my head. I could still hear. So you would actually hear better. The same thing, we have a learning system in the brain. So if you lose hearing on one ear, you will eventually learn how to use it, how to move your head, so you can figure out where. It takes a while. So this is what we do with MIMO, multiple input, multiple outputs. So it's the same thing. So both transmitters and receivers have multiple. So multiple mouths, multiple ears. So the more antennas you have, the bigger the gain. And in order for it to be, in order for you to use this diversity thing, you need to have uncorrelated channels. You need to have them half a wavelength apart. And the distance the antenna needs to be separated in order to be uncorrelated reduces with frequency. So when we had these wireless LANs, 2.4 gigahertz, it was only laptops that could have MIMO stuff. So one in each one. Cell phones, they were too small. But when we changed to 5 gigahertz, for example, it's easier to use MIMO because they can sit closer together. Yeah, and then there's different ways of using this multiple antennas. If you have antenna diversity, you just have multiple antennas. But you can have spatial multiplexing, multiple independent streams. You just increase the rates, send each one on a different antenna. Or you can send the same signal on all of them and listen to all and just select the best one and throw the other ones away. Same thing as you do with the ARQ, repeating, and you say it doesn't work, get me another one. But here you do the same thing, but at the same time. Or you can combine all of them, like majority voting thing. Or you can do coding on it. That's like a smarter way. This is like a repetition code, and this is normal, smart way of combining it. And even if you don't have multiple antennas, they figure out a way so you can still use it and have it. Or you can do this transmit beamforming. It's like a surround sound. Like when you sit in front of your TV, you put the speakers so that the sound is maximized at one specific point in your living room. So here we can do the same thing. Because we know the wavelengths are vary, so we make sure that they interfere constructively exactly at this point. So there it's really good. Around it is sort of outage. So it's the same. If you don't have space or room for different antennas, you can do relaying. So here we have more than one in the same package. So we have space diversity because we retransmit at a different place. And also we have time diversity because we don't transmit at the same time. You can have this as well, but it's more difficult with relaying. And even here you can choose frequency diversity if you want to. So here you can do space diversity even though you have only one antenna on each one, but they cooperate to help each other. So the challenge for cyber-physical systems guys is that we get diversity for increased rate or range or reliability, but typically not at the same time. So some of these diversity schemes are not so good. Say if you use retransmissions, we increase the reliability, but also the delay and the jitter, which is important for some control guys. Frequency hopping increases complexity. So if you want to have really cheap sensors or $1 things, this is the cost. Frequency hopping is more processing. MIMO antennas, it gives us higher reliability, but also complexity and some form factor requirements, which could be problematic for some cases. So if you use relaying, it also increases reliability, but more complex. We need to coordinate among the different users. So most wireless protocols that exist today, they exist because somebody needed them. So for voice protocols, they exist because we needed to have this low delay things. Or wireless web browsing because we needed to have reliable, but not time critical. So all of a sudden there's things that needs to have both at the same time. So it hasn't necessarily been used. There have been some in wireless in automation. There has been a requirement for both reliability and time critical, but most field buses that are used for this, they are wired. So here, if we have connected cyber-physical systems, we need time and safety critical, and they need reliable wireless communication, but also that it's secure and energy efficient at the same time. So lots of things are happening, not just the requirements are evolving, but also the communications is revolving. So this Nyquist thing that causes intersymbol interference, we try to conquer it using better low-pass filters, very capable hardware. But hardware is improving. It becomes cheaper, software-defined, and fuzzy. All of a sudden, we can sort of sneak around Nyquist's back a bit. Same thing with channel capacity, Shannon's. This is difficult for Swedes. Shannon's channel capacity. So we try to do exhaustive search to find the codes that he says exist. So we found this, and then we connect them together. So we do iterative things, and when the finding codes reduces to curve fitting. We can also combine different blocks, like coding and modulation together, or modulation and equalization. Equalization to conquer this intersymbol interference. Coding and iterative detection. But you can also just do machine learning for the whole thing. Solved. No need to know any more math. So this is my maybe personal conclusion. So I think everything that considered to be bad previously, it can be used to an advantage. Because it's inherently broadcast, we've said that, oh, this is problematic because we've always been limited by this compared to cross-talking between wires. But now we know this about frequency and space diversity, we can actually use all the channels at the same time, the way it was intended to. So because we know what's happening in all the channels, we can make it interfere constructively. It's like having infinitely many cables at the same time, if we just know how to use them. And also they traditionally been said that as soon as you go wireless, it becomes more problems with security because it's inherently open. So you can have eavesdropping and jamming. But here we can use space diversity to divide the packet into different little pieces, sneak around with relaying. So we just go behind the back of the eavesdropper or the jammer. We can do smart frequency selection to avoid the jamming, or reduce the power of everything, so it goes below the noise threshold, or use a friendly jammer if I know what I'm gonna transmit. So let's say that I want to talk to Carl, and we are friends, and then we are also friends with Valid, but we don't want to talk to him right now. But because we're friends, we decided that he's gonna, whenever I talk to Carl, he's gonna transmit a jamming signal, a friendly one. So if we know which signal he's gonna transmit, there's gonna be no problem to removing that signal and extracting information. So as soon as I say, so now I wanna talk, and then you go, oh, and then I'm gonna talk, and then you have no problem removing the oh. But you have, now you became the enemy, sorry, because I don't know your name, that's why. So then he because he doesn't know the jamming signals, it would be more difficult for him to figure out. So this is something that and especially if you do this on a network level, not just a packet by packet level. So we take all the packets, divide it into different pieces, they will all take different parts, and then we do it with other messages and overlay them on top. It will almost be like blockchain thing. So you need to change lots of different things to work it. Okay, end. Look at the time.
Perfect. Thank you.
So I speak so fast, so you didn't have time to ask
I'm going to be
questions.
selfish and start with a question. So the last point, this jamming is almost like creating a shield around your channel actively, basically.
Yeah.
Okay. So that's another intuition, I guess.
Yeah.
It would be a valid intuition. Okay.
Yeah.
Good. Thank you. Other question?
Probably a mundane question. When you do frequency hopping, how does the receiver know what frequency you hop to?
So this you need to decide before you start. So most of the time it's decided in the so like Bluetooth, it needs to connect. Right. So you need to find the devices, and then at the same time it decides, okay, I'm going to use this hopping sequence. So if you want to talk to me, then you use this one.
So it broadcasts the hopping sequence?
Well, when it connects. That's why it has this password protected things in the beginning. Mm. When you do
so it just sounds so secure.
discoverable now thing, So then you need to do this on this. This is because now we're exchanging these hopping patterns. So I guess if you go in a factory or something, you do this first and then you go,
That sounds like a weak link in security.
Well, you can do it when you start. So you can connect them with a wire, exchange the hopping sequences, same way as you exchange keys and things. And then you have them and you separate them and they can be used forevermore.
So a related question, what does 8211 doesn't do that? The frequency hopping.
Some of the letters does.
Oh, okay.
And I forgot which
some
one.
of the variations do. Okay.
Yeah, some maybe.
But my regular one at home doesn't do that because when I switch on the microwave, it doesn't work.
Ah.
So.
Then I would change microwave because your body will. Yeah. You're supposed to. You can put your phone in the microwave.
Yeah.
Close the door. Don't start, and then try calling it. If it calls in there, or if it then you need a new microwave because that goes actually 2 gigahertz. Yeah. So it should be screening enough.
So it shouldn't happen.
So
most of the microwaves should do it.
You should block the ones because
they're dangerous microwaves. Does anybody else's microwave interfere with their?
So don't change your Wi-Fi. Change your microwave.
The Wi-Fi. Yours does too. Okay. It's not me. There's a whole bunch of broken microwaves out there.
Yep.
But it doesn't do that hopping.
Most of the ones they use, some of the, I think B uses direct sequence spectrum. It just flips it out over the noise floor, and then the other ones use OFDM, which is where you put the different. It's similar to frequency hopping, but you load little bits on mini frequencies, all of it. So it should be a bit more robust still. But I would change.
I'll let others also ask questions.
In Bluetooth, after you set up the connection, is that protocol, or are there protocols that would then change the sequence that's being used and how it's hopping?
Yeah, the modern ones now, they have this blacklisting thing, so then they can communicate with the other one saying I'm having on a good frequency. They're saying I'm having a bad frequency with this box, so I'm going to use it less often. But sometimes they just randomize sequences and they send this randomization to whoever they want to talk to. It's the same thing as when you have your Wi-Fi picking different channels. The frequency hopping is the same. It can be considered different channels.
Other questions?
Lunch?
Break.
Oh, break.
Okay. Thank you very much.